So following on from the previous video, the second fundamental theorem of calculus allows us a new way of expressing a function. It allows us a new way of expressing a graph. Okay, so for example, we were on this. So I'm trying to express this graph here. By using the second fundamental theorem of calculus, we can jump to here. So me trying to express this graph here is like me trying to I'm trying to express this graph here, but you have no idea what this graph looks like. All that I've given you to work with is, in effect, the derivative to work with. So the derivative, you have to take my word for the time being that the derivative looks like this. So this thing here looks like this. Okay, so I'm trying to express a function here. I'm trying to draw this graph here. I'm trying to express this graph here, but all that I've given you to play with is the derivative, and then from this you have to somehow build up a picture to try and work out what I'm trying to express here. So when you look at this, if you read this, it is really the area from 0 to x here. So let's say this here is a. Okay, so this here is a. So looking at this. Our function is really the area from 0 to x. So it's really the area from 0 to a here. So it's basically this area here. Okay, so this area here, and then let's just say it's right there. So this is our capital F of x here. Okay, and then let's say now we are at a new place. Let's say B is here. Okay, so now looking at this is the area from 0 to B. So that's the area from 0 to B. So that's this whole area here. Now B is here. So that's this whole area here from 0. So from 0 to B is this whole area from 0 to B. Then it's going to be bigger. So if B is here, then it's going to be somewhere up here. Okay, and then now let's look at point C. The area, you're going to get an increase, but it's only a small increase. It's getting smaller and smaller. So the area from 0 to C would be 0 to C. So looking at this, it would be this whole area here. So this whole area here from 0 to C is, let's say C is here, it would jump to, let's say, somewhere around here. Okay, and then let's say D is here, and then D is here, and then looking at this, our original function, our function here is really the area from 0 to D. So it is looking at this graph, it is from 0 to D. It is the whole area from 0 to D, which will be slightly bigger because from here to here there's an increase in an area, but not that much in comparison to over here. But it is a small increase, so it would be something like this. Okay, so your graph, you're going to have to use this technique here to somehow slowly build up what the original, what the intended graph would look like. Okay, so it's a bit like me giving you this. So remember, the fundamental theorem of calculus 2 allows us to have a new way of expressing a function. It's a bit like me giving you this. Hang on, it's a bit like me giving you this. I've got a function here, f of x equals the integral, let's say from 0 to x here of t squared dt. It's a bit like me expressing my graph in this form here, but in disguise, all that I've given you to work with is that the derivative must be x squared. Remember, from here we can use the second fundamental theorem of calculus to jump to here. So I'm trying to express a function here, but all that I've given you is that the derivative must look like this. So from this you have to somehow build up a picture. So to build up a picture that, when I express a function in this form here, in effect, all that I've given you to work with is that the derivative looks like this, and somehow you have to build up a picture you have to somehow build up that picture. So you might be asking, why not just integrate this to get your, because if you look at this here, you can just integrate this to get the original function. So why don't we use the same process? Why don't we just integrate this and then express our function in, well, I'll explain in the next video. But as it turns out, that it's not easy to integrate this. I will explain in the next video.